Hello everyone and welcome to A+ Physics. I'm Dan Fullerton, and in this video we're going to take the 2015 AP Physics 2 free response questions from the exam and go over those one at a time. As we do this, I'd like to note up front that they have not released the correct solutions, the scoring guide to this exam yet. So quite possible I make an error or two in here. Hopefully they're pretty small, but at least you'll get an idea of how I might go about attacking these sorts of questions. So let's take a second and we'll dive right into question number 1. All right, question number 1 is a short free response question. Now, it looks like we've got a diagram here where we've got air, liquid, and glass inside a drinking glass, it says. Looks kind of like a beaker to me, but doesn't matter. So let's do a quick diagram of what we have here. We've got our glass there. Inside it, we've got a region of liquid. Pretty poor drawing, I know, but I think you'll get the general idea. There's our liquid. And up above that, we have air. So glass, our liquid, and air. And as we draw a normal line here, we have on our diagram an incoming ray that looks like it's incoming at angle theta 1. So there's our setup. It says we've got a cross section of a drinking glass that has an index of refraction of 1.52. So n equals 1.52 there, filled with a thin layer of liquid with an index of refraction 1.33. So our incoming beam is going to go from a high index to a low index. The bottom corners of the glass are circular arcs with the bottom right arc centered at point O. So we should maybe label point O there. There we go. Monochromatic light source placed to the right of point P. There's our point P. Shines a beam aimed at point O at an angle of incidence theta 1 here. Oh, comes in here at theta, comes in there at theta 1. All right, when this happens, when theta equals theta 1, we get two bright spots on the bottom surface of the glass. The spot closer to point P we're going to refer to as X, and the one that's farther from P we're going to call Y. And X and Y change as theta is increased. All right, so then it says, in a paragraph length answer, describe the processes involved in the formation of spots X and Y when theta equals theta 1. And explain why Y is further from P than X, and what factors affect the brightness of the spots. All right, so we've got a bit to do here, kind of a big question there all at once. The first thing I do in a question like this is try and figure out for myself what's going on before I try and write about it. So if we've got this beam coming in from high index to a low index, we know we're going to get some amount of reflection, where the angle of incidence equals the angle of reflection. So right away we're going to get a reflected beam. Now let's change the color of that. Let's make that bright pink so we can see it easy. We'll get some reflection right there, and that'll be one point we'll see on the bottom of the glass. Now, because we're going from high index to low index, we're also going to see some refraction away from the normal. So we're also going to have some of the beam, and I may be over-exaggerating this a bit. I don't think we have to actually even calculate the angles in this problem. We're going to have that happen. Then we go from high to low index again. So we're going to have some more refraction perhaps, but we're also going to get reflection at this interface. Angle of incidence equals angle of reflection, just drawing this out quickly. And as we go from low index to high index, we're going to bend toward the normal again. So some of the light's going to come out here. And as they've set up the problem, we are going to label these X and Y. So the way I would explain something like this, and I'm not going to write it out, you can write it out. I'd recommend even making a short outline before you actually go writing out your paragraph. Something like both reflection and refraction lead to the formation of spots X and Y on the bottom of the glass. As the initial ray of light travels through the glass, it reaches the glass-liquid interface with an angle of incidence theta 1. Some of this ray is reflected back at an angle of reflection which is equal to the angle of incidence, forming spot X where this ray reaches the bottom edge of the glass. The portion of the ray that wasn't reflected is refracted away from the normal as it enters the liquid, going from a high to a low index material. When it reaches the interface between liquid and air, some of this ray is reflected, where it travels back to the liquid glass interface, where some of it again refracts as it enters the glass with an index of refraction, with an angle of refraction theta 1. After traveling through the glass, it again refracts. After traveling through the glass, this ray finally forms spot Y on the bottom of the glass, to the left of point X due to the extra horizontal distance it had to travel in the liquid. The brightness of the spots is a function of how much of the initial beam reaches those various points. So we would expect X to have a decreasing brightness, Y to have a decreasing brightness, because we have some of this that's actually still traveling into the air, as well as you're going to have some absorption, a small amount, likely in all of these different materials. So I would say something along those lines to answer question 1. Now when we get to B, it says when theta is increased to theta 2, one of the spots becomes brighter than it was before due to total internal reflection. So we're increasing this angle from theta 1 to now we have theta 2. All right. On the figure below, draw a ray diagram that clearly and accurately shows the formation of spots X and Y when theta equals theta 2. Well, now what happens is we have total internal reflection, which means as this beam is refracted now, it's going to get to this point, and instead, previously, we had some of the beam in the air that was also, some of the beam in the air that was also being refracted into the air. So we lost a little bit of the beam's brightness there. Now, with total internal reflection, all of this beam is reflected. None is refracted into the air. So it's going to follow in like this and come back out there. So now we will have spots X and Y in yellow, and they've moved over. And you're going to see that Y becomes brighter because now you don't have any of this beam's intensity that's lost that is traveling into the air. It's all being reflected from the liquid to the glass and back to point Y. So which spot becomes brighter? Y becomes brighter as all light from point A is reflected. Now, some was previously refracted into the air. So then C, when theta is further increased to theta 3, one of the spots disappears entirely. So when this happens, we've now got an even bigger angle. Which spot disappears? Explain your reasoning in terms of total internal reflection. Well, I'm going to use a nice green color here, and I know this is getting kind of busy, but now we have incoming beam right there, and that angle there in green is theta 3. And because it's all completely totally internally reflected, not so good at saying that this morning, totally internally reflected, all of that beam's energy is reflected right back out. So there's our new point X now. No refraction into the liquid, none of that beam's intensity heading into the air. So Y would disappear. All we have is that first reflection point, X. Explain your reasoning in terms of total internal reflection. Y disappears. As the incident angle is increased to theta 3, eventually all the incident light at the glass-liquid interface is totally internally reflected. No light is refracted into the liquid. Therefore, all light is reflected to spot X. Spot Y can only exist when there is refraction into the liquid. With no refraction into the liquid, there is no spot Y. And I say that all of the light is reflected to spot X. Realize there's probably some amount of absorption and other things going on here as well. So that gets us through question number 1. Let's take a quick break. We'll come back to question number 2. Question number 2, a circuits question. A battery of EMF E and negligible internal resistance, 3 identical incandescent bulbs and a switch S, initially open, are connected in a circuit as shown. And that's drawn kind of funny. So I would probably start by redrawing this in a way that makes me feel a little bit better. We've got our source of electric potential there. We've got our first bulb, and I'm just going to draw it as a resistor for simplicity. We'll call that R1. And then it looks like we have 2 bulbs in parallel. We've got R2, And over here we have R3, which also has a switch. Switch labeled S. So I would probably redraw our circuit that way. The bulbs each have resistance R. Students make predictions about what happens to the brightness of the bulbs after the switch is closed. So, one student says, bulb 1 will decrease in brightness when the switch is closed. Do you agree or disagree with the student's prediction about bulb 1? Qualitatively explain your reasoning. Well, that pretty obviously I would disagree with. When the switch is closed, bulbs 2 and 3 operate in parallel, lowering their combined effective resistance, which results in a larger voltage drop across bulb 1. Therefore, more power is dissipated in bulb 1 because power is V squared over R, and power is related to the brightness of the bulb. Now for A2, before the switch is closed, the power expended by bulb 1 is P1. Derive an expression for the power P new expended by bulb 1 after the switch is closed in terms of P1. So if we look at the initial setup in our circuit, before that's closed, we only have to worry about bulb 1, bulb 2, and I'll make a row down here for total. And we have voltage, current, resistance, and power for those elements. And when we look at this, we know the resistance of each of our bulbs is R. And because this is open at the moment, what we really have is a series circuit, so our total resistance is just the sum of the resistances, 2R. And our total EMF is E, which means we're dropping half of that across each of those resistors. So E over 2, E over 2. Current is V over R, so this will be E over 2R, E over 2R, and of course E over 2R. It's a series circuit at this point, so the current is same at all points in the circuit. And power then, we could find a number of different ways, I squared R, V squared over R, or V times I. Regardless of your favorite method of calculating power for the different rows, I come up with E squared over 4R, E squared over 4R, and of course E squared over 2R. So that's our initial conditions. Now our new conditions, let's do another table now when this switch is closed and we've got R2 and R3 in parallel. So now we'll have B1, bulb 2, bulb 3, and our total V, I, R, and P. And let's just see what we get here when we go through this. We know that the resistance of all of our bulbs is still R. We also know our total EMF is E. So our total resistance, the resistance of bulbs 2 and 3, the equivalent resistance, will be R over 2. So we'll have R plus R over 2, or 3R over 2 for our total resistance. So we can find our total current flow, I equals V over R, which will be then 2E over 3R. That total current must be going through bulb 1. All the current has to pass through R1 as well as the battery. So that's going to be 2E over 3R. And then it splits and half goes through these identical resistors. So that will be just E over 3R and E over 3R. Well, now I can find the voltage drop across all of these elements. V equals I times R. So this will be 2E over 3. We will have over here E over 3 and E over 3. So now we can calculate the powers, and we're really only worried about bulb 1, so I can just do V times I and find that our power here is 4E squared over 9R. So if I want to know how the power new compares to the initial power 1, well, power 1 we had E squared over 4R. Now we have 4E squared over 9R. So our new power over P1 would be 4E squared over 9R divided by E squared over 4R. Our E squareds make a ratio of 1, our R's make a ratio of 1, and I will come up with about 16/9. So our new power is 16/9 of our initial power. So kind of the long way to go to get there, but I feel pretty confident in that answer, and I've got it numerically calculated, and I learned a lot about the circuit by walking through that. So A3, how does the result of your derivation in part A2 relate to your explanation in A1? Well, the derivation in A2 supports my explanation in part A1 as it confirms that the power dissipated in bulb 1 increases when the switch is closed and bulb 3 is introduced to the circuit. For part B, we've got another claim by a student. Bulb 2 will decrease in brightness after the switch is closed. Do I agree or disagree, and explain in words? Well, as we just said, I agree there. The voltage drop across bulb 2 will decrease when it's placed in parallel with bulb 3. We saw that when we went from the initial to the new circuit. Therefore, less power is dissipated in bulb 2, and power is related to brightness. And now we need to justify that with the calculation. I'll use the VERP tables that we made previously and use that as well. So our power 2 initial was E squared over 4R. And our new power 2, well, let's see here. Our new power 2 is going to be E squared over 9R V times I. So we went from E squared over 4R to E squared over 9R. That's a ratio of 4/9. So for 2B2, power 2 new equals 4/9 power, I keep writing R there, power 2 initial. While the switch is open, bulb 3 is replaced with an uncharged capacitor. The switch is closed. How does the brightness of bulb 1 compare to the brightness of bulb 2 immediately after the switch is closed, and justify your answer? Well, immediately after the switch is closed, bulb 1 is very bright and bulb 2 is very dark. All current through the capacitor, through the R2 capacitor parallel path, goes to the capacitor because that initially acts like a wire as it charges. And how does the brightness of bulb 1 compare to bulb 2 a long time after the switch is closed? Well, a long time after the switch is closed, the capacitor is fully charged, so it acts like an open. So, the circuit behaves then as if it were a 2-bulb series circuit, with each bulb at equal brightness due to identical current flows and voltage drops. So, something in words, write that out neatly, think through your answers, but you've got 25 minutes or so, it says, is their target time for this question, so should have lots of time to take your time and make a nice, coherent explanation for these questions. Take a quick break, come back to number 3. Number 3, our fluids question. Students are watching a science program about the North Pole, and the narrator says cold air sinking near the North Pole causes high air pressure. Based on the narrator's statement, a student makes the following claim. Since cold air near the North Pole is at high pressure, temperature and pressure must be inversely related. What do we think of that? Well, as I look at that, I would first say I would disagree with that. The student's claim erroneously generalizes a statement of fact. Sinking cold air causing high pressure at the North Pole does not, in and of itself, prove any general relationship between temperature and pressure. Now, if we look at ideal gases, we do find that temperature and pressure are directly related for a fixed volume of gas. This doesn't apply at the North Pole, however, where we don't have a fixed volume. So I would answer something like that to 3A. And now, after hearing the student's hypothesis, we design an experiment to investigate the relationship between temperature and pressure for a fixed amount of gas. We have a bunch of equipment available. What do we want? Well, I would probably pick something like the cylinder with a fixed lid, the one up there on the right, a pressure sensor, a basin that can hold lots of water, cold or hot, a source of hot water, a source of mixed ice and water for our cold water source, and a thermometer, and I think that would do it. Okay, now outline the experimental procedure you would use to gather the necessary data. Make sure it contains sufficient detail that someone else could follow our procedure. So this is really all about writing up lab procedures and designing experiments. Okay, so I would do something like this. I'd place the gas, likely air, in the cylinder and attach the fixed lid, so we've got our fixed volume. Insert the thermometer and the pressure sensors into the gaskets in the cylinder. Then place the cylinder in the basin and add ice water. As the cylinder cools, take and record readings of pressure and temperature in the cylinder. And depending on how fast it cools, it would tell you how quickly you should take those different readings. You don't need to take them every second, I wouldn't think, but enough that you get some differentiation in your data. When the temperature equilibrates at a minimum temperature, take a reading and remove the ice water, and now we're going to add hot water. As the temperature increases now, take and record readings of pressure and temperature in the cylinder again. And when the temperature equilibrates at its maximum temperature, take your final reading and stop. You should now have a great data set of temperatures and pressures. Now it shows the data that we got from a different experiment, which could have been our experiment, other than they've got some changes in volume here. What subset of the experimental trials would be most useful in creating a graph to determine the relationship between temperature and pressure for a fixed amount of gas? Explain why the trials you selected are most useful. Well, number one, because we're worried about doing this at fixed volume, I would pick all the data points that are at a fixed volume. And it looks like we've got lots of data points at a volume of 5 cubic centimeters, so I would just use all of the 5 cubic centimeter data. All right, so that takes us to part 3C. 3D says plot the subset of data chosen in part C on the axes below and label the axes appropriately. Draw a curve or line that best represents the relationship between the variables. So let's draw a graph, but we'll speed it up here so you don't have to watch me do this in the real time. All right, so when I make my graph, I come up with something that looks pretty linear, starting at temperature of 0 going up through 70, and I've extended my line a little bit further here. So, graph that looks like that. Note that I have temperature in degrees C down here and pressure in kilopascals. Typically what I would do is actually use kelvins here, just so we've got that baseline temperature scale. But degrees C works just fine as well, since that's what's given in our data table. E, what can be concluded from your curve or line about the relationship between temperature and pressure? I would probably go and calculate the slope just to make sure we've got all the data we want, because we could say something else. We could find our slope, pick a couple points on the graph. I might even go up here, pick 2 points on our line. I'm going to circle the points I'm using, and say the slope is our rise over run, which is going to be 70 kilopascals over 90 degrees C, which is 7/9 of a kilopascal per degree C, or 780 pascals per degree C. And I might say something like, there's a linear relationship between pressure and temperature in a fixed volume with a fixed amount of gas, where pressure increases approximately 780 pascals per degree Celsius. And I think that should cover you pretty well for this problem. All right, one more. Take a quick break. We'll come back with number 4. The apparatus shown consists of 2 oppositely charged parallel conducting plates with an area of 1/4 square meter, separated by a distance of 0.01 meter or a centimeter. Each plate has a hole at its center through which electrons can pass. High-velocity electrons produced by an electron source enter the top plate with speed 5.4 times 10 to the 6 meters per second. They take 1.4 nanoseconds, wow, that's fast, to travel between the plates, and leave the bottom plate with speed 8.02 times 10 to the 6 meters per second. So they're getting faster as they go through the plates. Which of the plates, top or bottom, is negatively charged? Support your answer with the reference to the direction of the electric field between the plates. Well, we've got our plates like this, and we've got our electrons going this way from V0 to V final. And if the electrons are accelerating down, that means the electric field must be in that direction, must be up. We also know that the negative electrons would be attracted toward the bottom plate, so that would mean that the bottom would be positively charged and that would be negatively charged. So which of the plates is negatively charged? For answer A, I would say the top plate is negatively charged. As the electron traverses the region between the plates, it speeds up. Therefore, the force on the electron must be downward, so the electric field must point up toward the top of the page, toward the top plate. The electric field runs from positive to negative charges, therefore the top plate must be negative and the bottom must be positive. So, quick way to answer 4A. For B, calculate the magnitude of the electric field between the plates. Well, a couple ways we can do this. I might go with the kinematics version. We know the initial velocity of our electron is 5.4 times 10 to the 6th meters per second, and its final velocity is 8.02 million meters per second. It does that in 1.49 nanoseconds, or 1.4 times 10 to the minus 9 seconds, and the distance it traverses is 0.01 meters. So using kinematics, I'll find the acceleration as the change in velocity divided by the time, which is our final velocity minus our initial velocity divided by time, which comes out to be about 1.76 times 10 to the 15th meters per second squared. Well, using Newton's second law, we know that force is mass times acceleration, which in this case, our force is charge times the electric field strength between the plates. Therefore, we can find the electric field strength is our mass times acceleration over charge, or when I plug in my values, my charge 1.6 times 10 to the minus 19 coulombs, the charge on an electron, I come up with an electric field strength of about 10,000 volts per meter, or 10,000 newtons per coulomb. Either unit would be acceptable. And C, find the magnitude of the charge on each plate. Now, before we do that, let's go on and let's do B another way here as well. Just because we can, besides going the kinematics approach, it might be fun to do it another way. We could also use the work energy theorem. Work is the change in kinetic energy, and since our work is charge times voltage, and the voltage between our plates is the electric field times the distance between the plates, we could say that QED equals change in kinetic energy. Well, that's going to be 1/2 mv final squared minus 1/2 mass of our electron v initial squared, or v0 squared, I guess, divided by, well, that'll work for delta K. So then, if we want just the electric field, we'll divide this by QD. Pull that, divide both sides by QD. And if we replace Q with our charge on our electron, there we go, 1.6 times 10 to the minus 19 coulombs, in our distance 0.01 meters, plug in our values here, we can also find that way that the electric field is 10,000 volts per meter. Just another path to that same answer if you're interested. Kind of a slick derivation there. And then C, calculate the magnitude of the charge on the top plate. Well, to do that, I would recognize that what we're really looking at here is basically a parallel plate capacitor, where capacitance is charge divided by voltage. Therefore, charge is capacitance times voltage. Now, our capacitance of a parallel plate capacitor is epsilon naught A over D, the separation between them. And the voltage across them, we just said, was electric field times the distance between them. Therefore, charge is going to be epsilon naught A over D times our voltage, ED, which our separation of the capacitors makes a ratio of 1, and we just end up with epsilon naught A times the electric field strength. Therefore, our charge is going to be epsilon naught 8.854 times 10 to the minus 12 coulomb squared per Newton meter squared, times our area, given in the problem as 1/4 of a square meter, times our electric field strength, which we just found is 10,000 volts per meter, or 10,000 newtons per coulomb, for a total of about 2.2 times 10 to the minus 8 coulombs. All right, let's go to the next page to finish up this problem, to go to part D. Give ourselves some more room. The electron leaves the bottom plate and enters the region inside the dashed box shown below. It contains a uniform magnetic field of magnitude B that's perpendicular to the page. It then leaves the magnetic field at point X. On the figure, sketch the path of the electrons from the bottom plate to point X. Explain why the path has the shape that you sketched. All right, as I look at this, because the electron enters a uniform magnetic field region, the force on the electron is always perpendicular to its velocity and constant in magnitude. Therefore, the magnetic force is going to act as a centripetal force, pulling the electron in a circular path. So if we have our plates again, and our electron, once it gets here and is leaving the plate and entering this magnetic field region, let's draw that in very lightly. Well, we're going to get a portion of a circular arc over here to get to point X. Now, indicate whether the magnetic field is directed into the page or out of the page. Briefly explain your choice. So this is going to be a right-hand rule problem. And I'm going to do this with the assumption, since it's a negative charge, I'm actually going to use my left hand. I point my left hand in the direction the electron is moving, down, and I bend my fingers in the direction of the magnetic field. I've got two choices, into or out of the page. So, as I want the force, my thumb, to end up pointing to the left, I have to point my fingers out of the plane of the page to have my thumb point this way toward point X. So I would answer out of the page. Using the left-hand rule, since the electron is a negatively charged particle, I point the fingers of my left hand in the direction of the electron's velocity, which is toward the bottom of the page, and bend my fingers of my left hand inward, which is out of the plane of the page, leaving my thumb to point to the right of the page in the direction of the force that would cause this acceleration to cause it to move in a circular path, which is toward the center of that circular path. It's a centripetal force. So correct answer, out of the page. All right, that concludes the exam. We went through it fairly quickly, but hopefully it gives you an idea of what they might have been looking for, or at least one path to reasoning your way through these answers. Thank you so much for your time, everyone, and make it a great day.